I'm a content of Skymath, and I'm here again to discuss one of the key areas in physics for WASC, JAM, and as well as in ECHO. The topic is clearly wave-particle paradox. Wave-particle paradox, the areas we are going to consider for this lesson will be on three areas: dual nature of light, the Broglie's wavelength, and the uncertainty principle. These are the key areas. I hope after going through this video, you'll be able to answer any question you come across, either being it WASC, NECO, or JAM, or any other related examination. You see, so this lecture will give you a broader scope on your preparation for your WASC exam. So, considering these topics, we start with the first one, which is dual nature of light. So, dual nature of light is in two ways. This one, dual tells about two things. You see, so it simply means how light behaves in two things. What are those two things? Light can either be as a wave or a particle. So these are the two things which this whole topic is trying to tell us about. So dual means there are two things that are going, but not simultaneously. Light can either be as a wave or as a particle. So if you are asked during your exam, what does it mean by dual nature of light? Dual nature of light simply means light behaves in two forms. Light can either be as a wave or as a particle, but not as both simultaneously. Light cannot behave at the same time being a wave, the same time being a particle, but it can either be as a wave or a particle, but not as a wave and a particle simultaneously. So that's what it meant by dual nature of light. Now, when light behaves as a particle, what are the characteristics? One, when light behaves as a particle, so what are the properties? So the properties here, when light behaves as a wave, some of the things we have to take note of, there is reflection. You see, so the other point, there is refraction. The other point, there is diffraction. The other point, there is interference. So the next point, there is polarization. The sixth point, there is something like Compton effect. The next one is the black body radiation. So these are the observations we have to come across, or we have to capture. When light behaves as a wave, when light behaves as a wave, what are the properties we have at the end of the day? So when light behaves as a wave, these are the properties. You know, a wave can reflect, a wave can refract, can diffract, can interfere, can polarize, can occur as a Compton effect, that can as well as move in the form of black body radiation. As I said, dual nature of light simply tells about light behaving in two ways. Light can either be as a wave or as a particle. So when light behaves as a wave, these are the properties. So moving to the second case again, when light behaves as a particle, what are some of the things we have to capture? So when light behaves as a particle, one of the things we need to capture, since the particle is moving from one point to another, it possesses mass and as well as it has a velocity. So multiplying the product of the mass and its velocity, that yields also momentum. So this light of this particular particle, it possesses momentum. The next point, it also possesses photoelectricity because it's in the form of photons. The next point, it also has the process of absorption of light. And the last point, which we have to take note of, is the energy, which can refer to as radiation of energy, let's say from hot bodies. Radiation of energy from hot body. So these are the properties or the characteristics or the features when light behaves as a particle. It takes the process of momentum, a photoelectricity, the absorption of light, radiation of energy from hot bodies, which is the photons, which we are going to derive one of its equations before the end of the video. Now, the next case again, dual nature of light simply tells about light can either behave as a wave or a particle, but not the two properties at the same time. So capturing this, the other point again you have to take note of, how can we measure these values? So we have what we call particles used in explaining the wave dual nature of light. So the particle used in explaining the wave dual nature of light, one of those particles we have electrons, you see. So the other point again we have neutrons, and the next point we also have something like helium nuclide. We also have helium atom, and let's say the last one we have the proton or hydrogen atom. So maybe if we can represent their respective symbols, electron, it possesses a negative, neutron has a mass of 1 and atomic number of 0. Helium nuclide we can put in the form of 4, 2, and helium atom just like He, and the proton can be, it has a mass of 1, atomic mass of 1 and the atomic number of 1, or its hydrogen atom, the same thing, atomic mass of 1 or mass number 1 and atomic number to be 1. Also, this helium nuclide, you can also possess this to be the alpha particle, which you can write as 4, 2. So these are some of the things you have to capture for your WASP examination. The particles used in explaining the wave dual nature of light, electrons, neutrons, helium nuclide, helium atom, proton, or hydrogen. The other point again, which is also sensitive here, we have what we call devices. Devices whose invention is based on dual nature of light. So we have two of those. We have the scanning tunneling microscope. So this is one of the devices you have to take note of. The other device again, we also have the electron microscope. So these are some of the things you have to take note of. So under this topic, wave dual nature of light, these are the sub points you have to take note of. Wave behave as a particle and as well as a wave. Light behave as a particle and as well as a wave. When it behaves as a wave, you have to know the properties. When it behaves as a particle, you have to know the characteristics of the properties. So the other point again, particles which you can use in explaining this dual nature of light, these are these, and the devices or the apparatus based on dual nature of light, these are the points. So this is just the basic end of dual nature of light. So if we move to the other points again, which we refer to as the Broglie's wavelength. When we consider the Broglie's wavelength is in two conditions. The Broglie's wavelength. So the Broglie wavelength, this man tells us that the wavelength of a particle, when this wavelength has a linear momentum, it clearly tells us that the wavelength of this particle is inversely proportional to its momentum. So this wavelength, the Broglie's wavelength of a particle is inversely proportional to its linear momentum. So this man tells us about that. Any particle with a linear momentum, it possesses a wave nature. And when it possesses a wave nature, it further tells us that this wavelength of that particle is inversely proportional to its linear momentum. So if we remove this proportionality, we have wavelength to be h all over p. Where this is the wavelength, p is the momentum, and h is the Planck's constant. You see, where we have this momentum to be equals to mass times v, or mc, or which you can as well put as hv, hf all over c. So, but if we try to have another similar derivation from Albert Einstein's famous equation, which we can put in this way: e square m square c raised to power 4 plus p square c square. But this, we can simplify it as this format. So let's call it equation 1. Now, if we target on certain areas, let's say we consider the energy of momentum, which is Pc all square. We equate this energy to this energy. That means the particle is moving. When the particle is moving, it possesses linear momentum. So let's say if this square cancels this square, we have this energy to be Pc. You see, so therefore E equals more P, we have it to be what? Hf all over C, which is Hf all over C times C. So C cancels C, so then energy equals to Hf. So this gives us equation 2. So moving forward, we consider again this energy in terms of its rest energy. So when the rest energy is considered, we have mc squared all squared. When the rest energy consider that E square equals to this value, so if this square equals to this value, the common power here is 2. So if 2 cancel, we have E equals to mc squared. But this energy, we can be simplified as mc times c. We are in energy going to this mc is P, as we illustrated it here, P equals to mc, and this c can as well be given as, we say, but c equals to f lambda. From, if we refresh our mind, we have the speed of light to be f lambda, which can put c equals to f lambda. So this energy, mc is p times c is f lambda. So this gives us equation 3. So equating equation 2 and 3, equating equation 2 and equation 3, that if this energy of photons equals to the rest energy E, we can say Hf is equal to Pf lambda. So therefore, carefully, F cancel F, we have H equals to P lambda. So if we make lambda the subject, we divide by P, we divide by P. This carefully cancel. So we have lambda to be H all over P as equation 4 as we have here. This is another short way of having it. So this tells us that the greater the momentum, the lower the wavelength, or the lower the momentum, the higher the wavelength. This one way. So another way of having this relation, let's say in terms of the wavelength, its kinetic energy. So let's say we take relationship between m u the potential difference and kinetic energy half me u squared. So we take this relationship. Let's say a particle of mass ma has a velocity u with a particle of mass ma has a velocity u with kinetic energy to be as rmu squared. So in this case, how can we have the relationship between the mass of this particle? Let's say the particle is an electron, because this particle can be an electron. So if you have this particle as an electron, and this electron has a mass of ma with a velocity of u, and it possesses kinetic energy because it's a moving energy. So how can we have a relation between m, u, and v? But in this case, we have to consider in two ways. We have the energy equals to the ev, and we also consider the energy of the moving electron, which is in terms of the kinetic energy, which is m half mv squared. But here now, our v is going to be u, which is u squared. But since we consider electron, it's going to be mass of the electron, ma. So this is going to be electronic. This is for electronic charge, which has a constant value, and this v is the potential difference, which is the voltage. So equating these two values, we have ev. This implies ev equals to this, which is half meu squared. If we cross multiply, we have 2ev equals to meu squared. If we divide both sides by ma, this carefully cancel. So u squared is going to be 2ev over ma. Let's say this is equation 4. So having this equation 4, the next points we have to move to, let's say this point, let's just consider this as equation 1. If we have this as equation 1, so the next point, let's consider the momentum of this particle. Before we consider the momentum of this particle, let's take the square root of this. So consider the square root is going to be 2ev all over ma. So therefore, momentum now P equals to mass times the velocity. But the mass now here is going to be the terms of mass of the electron times the speed of the electron. So P equals to me times, what is u is this, which is the square root of 2ev all over ma. So in this case, let's see the mathematics here. If we put this value inside, what will happen? If we put this inside, it's going to be squared. So it's going to be me squared times what we have inside. We repeat it. So you know, this square will cancel this ma. So this momentum can be equals to 2e ma v squared. So we have this value. Okay, so we have P equals to square root of 2e ma. This is momentum. But we have the wavelength of the particle to be h all over what? Lambda. H all over the momentum. So this wavelength is going to be h all over what the momentum is this? This is equation 2. So substituting the momentum, which is the square root of 2e mev. So this gives us equation 3. So if you go through what I have explained up to this point, I guess there will be no question which you cannot be able to conquer during your exam period with respect to wave particle paradox. This is just a basic point. So let's try to look for one or two basic problems. If we consider these two examples, we have this example says, if electrons are vacillated from rest through a potential difference of 10 kilovolts. Let's have our data. The voltage is 10 kilovolts, but we have the 10 times. You know, this kilo is a factor which has 1000 V, so which you can put as 10,000 V. So, what is the wavelength of the what is the wavelength of simply the isolated electron? We are required to find the wavelength of the isolated electron, but we are given the mass of electron to be 9.1 times 10 to the power 31 kg, and as well as the electronic charge, which is 1.6 times 10 to the power minus 34 joules second. We are required to find the wavelength of this particle. But here, without wasting time, let us recall from this equation the wavelength of the particle is this. So if we substitute this wavelength, it's going to be h all over the square root of 2e MeV. So we substitute h now h is the Planck's constant. We are required to find the wavelength of the particle. Well, h now is the Planck's constant, which is 6.6 times 10 to the power minus 34. This Planck's constant, it has a constant value, which is this, divided by the square root of 2 times the electronic charge E is given as this, 1.6 times 10 to the power minus 34 times the mass of electron, which is 9.1 times 10 to the power minus 31 times the voltage, which is 10,000. So the wavelength of this particle will be like, so the square 6.6 times 10 to the power minus 34 divided by the square root of 2 times 1.6 times this times 9.1 times 10 to the power minus 31 times 10,000. We have the wavelength to be 1.22 times 10 to the power minus 11 meters. So this is the wavelength of the isolated electron. So if we go into question 2, question 2 again, we have the mass and wavelength of the moving electron. We have the mass given as 9.0 times 10 to the power minus 31 kg. We also have the wavelength to be 1.0 times 10 to the power minus 10 meters. So the Planck's constant is given, which is constant, minus 34 joules second. We are required to calculate the kinetic energy. But if we calculate the kinetic energy, you know the kinetic energy of this electron is going to be R times mass of electron times the speed of electron squared. But we don't have U. But we have momentum to be mass times the velocity, which is the mass of the electron and the speed of the electron. We also have this momentum to be, h all over lambda. So if you equate the two, h all over lambda equals to MEU. So if making U the subject, you're going to be h divided by ME lambda equals to U. Let's say this is equation 1 for this question. So if we move forward, we can also able to summarize here U equals to h all over ME lambda. But what we have here as kinetic energy is U squared. So therefore we squaring this U for the left hand side, as well square this again on the right hand side, all square. Right? So U squared now is going to be h squared ME squared times lambda squared. Let's say this is equation 2. So if you move now this implies kinetic energy, which is R mass of the electron, speed of electron squared, which can calculate it as R ME times what is U squared is this. U squared is this value. If we substitute it here, we have h squared all over ME squared lambda squared. So kinetic energy R times, you can see ME cancel one of this. So it remains h squared all over ME lambda squared. I think we have all what we are looking for. So to slot these respective values, we have h, this can be same as h squared all over 2ME lambda squared. So h now is this, which is given as 6.6 by 10 to the power minus 34 squared, divided by 2 times the mass of the electron is this, which is 9.0 times 10 to the power minus 31 times the charge wavelength of the electron is minus 10 raised to the power this all squared. So the kinetic energy of this value will be like square root of 6.6 times this divided by 2 times 9 times this. So we have the value to be 2.42 times, you can say 10 raised to the power minus 17 joules. So this is just the basic way of solving this. So these two examples are enough. So you can look for more examples. So thank you for going through this video, and I hope going through this video have given you more concept. Thank you all. Stay blessed.